project presentation for the microprocessor design project, which was to basically monitor a simulated signal, which basically simulates the output from a industrial piece of equipment, and that was of a sine wave. The system was to monitor the waveform on an 8051 processor. And check that the frequency and magnitude of that signal were within tolerance. If not, they would light a warning LED to inform the user that the system had malfunctioned. So I'll go on. This is the initial project plan. So the group, it was actually a group project between myself and another member. So you can see the yellow is joint work, green team member 1, blue team member 2, and then that splits it up, and then you've got like the meetings, which is shown up with the numbers in the yellow, and the Christmas vacation in red. The aim really was before Christmas, or in term 1, was the investigation of the circuit components and operation and the design in ISIS and test the programming. The Christmas break was to complete the area's PCB design, and term 2 focused on actually building the PCB and then the main programming and checking the software and writing up the report and everything. So the design specification, as I say, was to monitor a sine wave, which was a 20 Hz signal at plus and minus 1 volt peak to peak. And then we had to design a daughter board to connect onto the expansion port of a teaching and development board, which is on a 8051 microcontroller. So you can see the analog input comes in on the picture on the top left. It's amplified, filtered, and then an ADC converts the analog signal to digital for the microcontroller. So you can see obviously the amplifier then amplifies this signal up to the desired voltage, 5 volts and 0 volts. You've also got a latch module on there, which is controlled by the microcontroller to output the data in parallel to a partner group board, and then obviously the data from their board would come back into our board so that the two signals could be compared in the future for the phase between them. The filter is for anti-aliasing, 100 Hz cutoff, and 4th order butterworth with a 24 dB per octave attenuation. The signal is to be sampled at 800 Hz, and then a running average of 4 samples is taken and output the computer at 400 Hz. So you would take 4 values, output those values, take 2 more values, and then output those 2 and the last 2 values from before, and keep doing that process. So you'd average 4 every 2 samples to get the 400 Hz. And then detect if the voltage falls below 0.5 volts for 1 second, or the frequency strays by 10% for 5 seconds, then signal an error to LEDs on the board, which is shown by the mouse pointer there. So there's one LED that would be on all the time, and one that would light when a fault occurs. Like I say, the bidirectional communication with the partner board to send and receive parallel data for use in comparing the 2 signals. So the analog design of the system, the Butterworth filter, was computed in ISIS, which is shown on the screen, and then on the graph on the left-hand side shows the attenuation that was required, and then the red shows the phase shift, and the calculations are on the left-hand side. This is the digital design. So you can see you've got the 2 LEDs, so the one would be on all the time, and one to signify the warning. In the top left is the top, pretty near the centre of the screen towards the right, is the ADC. The reference of that is set by a 4.7 volt Zener diode circuit with a capacitor for smoothing that voltage just to make sure it was stable. And then you've got the latch circuit here, which then outputs to the port on the board, which is connected. So one side of this connects into the bus, which connects onto the R board, and the other port here would connect onto the daughter board via a ribbon cable that was constructed, and then obviously their signal would come back in on this side so that the data could go crossways through the 2 boards. So this shows the PCB design. The main connection here is a 3-way socket, so it's basically 3 rows that would come off, slot onto the board. This is where the connection would go to the secondary board. This is the analog filter stage circuit here, and then this is the ADC and latch down in this corner with the transistors for the and resistors for the LEDs, and the red things signify links on the top of the board, where basically tracks on the blue side which underneath couldn't get through to the chips. So there's a total of 6 links on there, as you can see. And then you've got the decoupling capacitors around the board near to the power levels of the chips to ensure smooth signals. So the construction obviously started in the top right, drilling the holes in the PCB, and then basically fitting the components, making sure the components were put in the right way around, and make sure the LED were the same, put in the right way around. That shows all that. So this picture shows basically just after the holes were all drilled, the first components going in, which was the capacitors. So starting really with the smaller components, which are easier to solder in. There's no service mount chips or anything like that. So yeah, this is the completed board with the LEDs. This is where the signal and power come into the board externally. So some of the chips are powered by the 5 volts from the 8051 microcontroller, but these basically give the power into that chip, or the analog side of the circuit, the plus and minus voltage for that, and the sine wave to come in from the frequency generator. So this is just testing the circuit, making sure there's no short circuits, looking through magnifying binoculars, so zooming in, and then obviously trying the continuity check with the multimeter, and checking all the power lines around the board without the ICs, so the integrated circuit chips fitted, to make sure that there was no problems, making sure that all the voltage levels were correct, so that we wouldn't damage any of the chips that were going on the board. And then really ensuring that the board did not draw excessive current from the power supplies without the chips fitted, and then with the chips fitted. This is the testing of the filter. So we put the signal in, adjusted the frequency and measured the magnitude of the output to give us the rough attenuation to make sure that it was in line with the specification, which was the 100 Hz at the -3 dB point. So the circuit testing, ADC and sampling, basically the system was set up and checking that the analog to digital converter was given the right values. So obviously we had the stable reference. We could then put in basically a voltage level into it, check the output and see if that related to the value that we put in, and also making sure that the starter conversion and chips signal pins were being controlled by the PAL, which is the programmable logic on the board, which was programmed via like an EEPROM programmer, and then making sure that the values, like I said, that we received back were then correct. The output from the 8051 microcontroller was then output via the RS232 serial port into a software package called National Instruments LabVIEW. We had basically a serial application on there that inputs the data and graphs the data, so we could see the sine wave on there in real time. And then it also had some on-screen LEDs that, if certain conditions were met, so if there was a fault occurred, we could then output certain values, and if LabVIEW sees those values consecutive, so say a certain value over a time that it would never see in real life with the sine wave, then we knew that the fault had occurred, and it would light up some on-screen LEDs on the front panel on the LabVIEW program. And then once this was working, we used the spare timer, other than the one used for serial, to ensure that the sampling was done as per the specification. So this controls the flash of the LED also for the fault occurring. So the averaging, like I say, we took, so first example, we took 2 values, average those 2, 3 and 4, average those 2. The addition of these 2 divided by 2 would then give you the final average, first one. You then take 2 more values, 5 and 6, gives you this average, which you then add to the previous average, and then this process would occur continually. So this was checking for the errors, the voltage checking. Basically, we did this by, if the final average value is found to be under 180, which is 0.5 volts for 1 second, i.e. for 400 samples, as we were sampling with a frequency of 400 hertz, then the error will be detected and the light goes onto the screen on LabVIEW via sending the values. As you can see, the graph goes up here, sending a continual set of 255 values, which is the maximum value for one unsigned byte, being sent through and signifies the error. And then we did the same process with the frequency, where we basically checked the number of peaks and troughs in 1 second. So if you check here and here by basically checking the gradient on the waveform, then there should be, obviously for the 20 hertz, there should be within, I think it was 36 and 44 to be within the 10%. If it counted that many, then obviously it was okay. If it went outside that range for 5 seconds, then it would signify the error. So the program basically checked for the amount. If the amount within 5 seconds was ever found within that value, it would then reset the counter, and only if that counter got to 5 would it know it had occurred for 5 seconds in a row. So this shows the board with the ribbon cable, which would connect to a partner's board. We've put in, as you can see, some wire links as a sort of feedback system, so that the output from our latch is then fed back into our board, which we can then graph ourselves to check that this system is correct without a second board. And this was tested and basically working correctly, showing the latch was operating correctly. And this shows the final project plan. So it can be seen basically what went in. Yellow shows on schedule, red shows the things that were slightly behind schedule, blue is stuff that was really added that we didn't really plan for, and then green is stuff that was finished earlier than schedule. So you can see it went reasonably well to target a few things early and a few things late, and obviously a few more things which may have delayed this process that we hadn't really fully accounted for, or hadn't really accounted the amount of time that they would take. So you can see down here we've put underestimated the amount of coding required, and also the component research and on the ISIS simulation and PCB design took longer than expected, leading to all programming was carried out in the second term rather than starting the basics of it within the first term. And then this is the references. Thanks for watching.